Good afternoon, everyone. Welcome and thank you for attending the third HIT Wrap-Up Europe webinar. I'm John Kapatanakis, member of the HIT Wrap-Up Europe team at Aalborg University, Denmark. We are hosting a series of webinars about the HIT Wrap-Up Europe project funded by the European Union. This is the third of 7 webinars scheduled for spring 2018, while more will follow in autumn. At the webinars, we dive deeper into different aspects, methodologies, and findings of HIT Wrap-Up Europe. Today, Vad Mathiesen, professor at Aalborg University and coordinator of HIT Wrap-Up Europe, will provide a brief overview of the project and set the frame of today's topic. Then, Andrei David, PhD fellow at Aalborg University, will talk about large-scale heat pumps. Afterwards, a discussion follows with a first comment from Thomas Novak, Secretary General of the European Heat Pump Association, a HIT Wrap-Up Europe project partner. We'll have some time to answer your questions then. You can send these in the GoToWebinar sidebar on the right of your screen. Brian, over to you.
Thank you, John. Welcome to the webinar. Today we will talk about the role of large-scale heat pumps in future energy systems and the role we anticipated will have in the Heat Roadmap Europe project. The outline is that first of all you will be introduced to the overall project, and then we will go more into detail about what the current status is on large-scale heat pump with the purposes of supplying heat for buildings. For Heat Roadmap Europe, we're going to put the heat pumps into the overall energy system context. And just to introduce the Heat Roadmap Europe project, the aim of the Heat Roadmap Europe project is to create a scientific evidence to support long-term energy strategies at a local, national, and EU level in order to empower stakeholders and citizens to make a transition to a low-carbon energy system. Of course, with the focus on heating and cooling. And we shall do so by quantifying the impact of various alternatives within the heating and cooling sector. For us in the Heat Roadmap Europe team, it's important that we do not see the heating and cooling sector as a separate entity. We see it as part of the overall energy system, which also means that the way that we look at this, we also address the impacts on the electricity and the gas sector and the dynamics hour by hour when we change the supply system or do energy savings and energy efficiency on the building level. By the end of the project, the aim is to have covered 14 of the largest member states in EU, which represents 90% of the heat demand. Right now, our energy system looks like this. We are in a situation where we have several demands within mobility, electricity, cooling, and heating. And most of the time we supply this by providing fossil fuels. And in order to address when we need to fulfill an end demand and when it has to be produced, we have full flexibility in the fossil fuels that we put in on the resources side. In the future, it is clear that if we want to decarbonize our energy system, this needs to change. This also means that we need the flexibility elsewhere in the system. And a new system that we focus on here is to do energy savings in buildings and combine this with a new approach across the sectors within the energy system, where we address that in a future smart energy system we will have a lot more renewable energy sources from wind and solar, from geothermal, from bioenergy, that will create a completely new system, and in which we need interactions between the different parts of the energy system. So the aim in Heat Roadmap Europe is to use novel data about the heating and cooling sector, use new tools, and then provide energy strategies for the European member states towards 2050. One of the results you can already find on our homepage is related to how the heat supply, or what the size of the heating and cooling sector is compared to other parts of the energy sector. And what you can see here is that in all of the member states, heating and cooling is actually the largest share of the overall primary energy demand. What you can also see is that it's not only in the north or the cold north that we have a large share of heating and cooling demand. It is actually also in the south part of Europe. The mapping that has been done in Heat Roadmap Europe for 2015 here, or it shows also that the overall cooling share is lower than what you may anticipate. It is around 10 to 15%, and in all member states it is lower than 40% when we look at the heating and cooling demand together. And this means that addressing the heat demand is extremely important if we would like to decarbonize the overall energy system, but also, of course, cooling can take part. When we look at the overall situation, heating and cooling is around half of the energy demand in Europe, of which space heating is quite a substantial part, as well as process heating. A lot of the heating that is being provided today is covered by fossil fuels, around 66%, and only around 13% is provided by renewable energy. When we look in the future, it's important to look into all aspects of the heating and cooling sector. And if we look at this from the point of view of buildings, we can divide this into three main areas. One area is the thermal performance of buildings. Here we need to assess whether or to what extent we should insulate our houses and make further energy efficiency improvement that will decrease the demand at the house or industrial level. And then also we need to compare this refurbishment and energy efficiency measures to the costs of providing this with renewable energy. And these balances are quite important to address, and is something we will look into in Heat Roadmap Europe. Also, there's then the building operation and user behavior, and here it's important to notice that although we can calculate and make some recommendations, the actual use may be different. The third element is the new energy mix, energy supply mix, and here we have also heat pumps on both the district heating level and of course also on the individual household heat supply level. And in looking at this at the overall level, it's important to identify what the synergies are between the thermal performance of buildings and the new energy supply mix. In this report that is illustrated here, there are some results from previous research about these three elements. Heat Roadmap Europe builds on 3 previous studies, and in these studies we have found that heat savings needs to be performed everywhere, but that there is a balance between savings and supply. 30 to 50% is what is in general recommended to do at the end use level regarding savings. In urban areas, the general recommendation is to supply 50% of the heat demand with district heating, and in rural areas the main recommendation is to provide the remaining 50% of heat with heat pumps, individual heat pumps, and possibly solar thermal and bioenergy. In this Heat Roadmap Europe study, we will quantify this at the member state level, and in order to do so, we need to address the different elements needed, or we need to investigate the data needed to make scenarios going into the future. Already now we have quantified the 2015 heat demand and characterized this in each in a great detail, and also there has been saving potentials made on each member state. Also, we have completed a rather extensive mapping exercise, and available online is the PETA-4 GIS maps, where it's possible to go into a city or a country and zoom into 100 by 100 meters to assess the potential of district heating. And we are using this in the energy system analysis to know what are the costs of expanding or changing the heat supply system going into district heating. Then we have the overall energy system, which is also important, and using all of the data on the energy systems and the mapping and the building level savings potentials, it's possible to complete some energy system analysis where we create the Heat Roadmap Europe alternatives. Now, if we move into the district heating part, heat pumps have a role in the future supply of district heating in Europe, in combination with other supply systems. This illustration here shows the different generations of district heating, going from steam to what is in most countries at the moment the third generation district heating, and also looking into the future in the 4th generation district heating. If we look at the system dynamics, it's important to understand that if we, for example, have expanded our district heating share, this does not mean that it's only large-scale heat pumps that should provide the heat, but heat pumps have a role in connecting, so to say, the electricity sector with the heating sector. The overall supply in a district heating grid should be comprised of several sources, where large-scale heat pumps could supply between 15 and 25% depending on the local circumstances. In a future energy system, there are plenty of sources to supply district heating. In Heat Roadmap Europe, we have mapped the level of excess heat from industry and electricity production, and across Europe, these potentials are extremely high. The excess heat potentials in combination with geothermal, waste incineration, large-scale solar thermal, as well as combined heat and power, can make a puzzle that completes the district heating supply system. In the future, it's important to have flexibility in the heating system, and this is where heat pumps have a key role. For CHP or combined heat and power and heat pumps, as well as other sources, a thermal storage at the district heating level can provide the flexibility needed in order to be able to also integrate fluctuating renewable energy sources on the electricity side, such as wind and PV, as well as sources on the heat side, such as geothermal or solar thermal. Already now, it is clear in the third generation district heating systems that heat pumps can play a major role. And actually, looking at some of the state-of-the-art energy systems, we can also see that heat pumps are providing heat in existing district heating systems. Just to illustrate how already now this can take place, we'll go back to this smart energy system diagram that I showed in the beginning. And here it is illustrated how a heat pump can provide the flexibility needed in order to meet the heat demand at the right time, but combining the heat pump with the solar thermal when there's wind power in the energy system. The alternative to integrate a lot of electricity from renewable energy sources is electricity storage, which is significantly more expensive. And now I would like to give the word to Andrei David.
Hello, everybody, and thank you, Brian, for the transition to my part. I'll go ahead and start my presentation with the diagram where Brian left off, the diagram of a future smart energy system, where, as he explained, the heat pumps have a central role. They have the role of connecting the electricity sector with renewable wind and solar with the heating and the cooling sector, but also working in close combination with technologies such as combined heat and power or thermal storage. Now, in this such a system is what we expect to have or we would like to have in the future. And since heat pumps have such an important role in the system, it is also important to understand what is the current technical status and situation of the heat pumps nowadays, so we can better know what to expect, what to expect from the future, but also how to prepare for the future. That is why we developed a study at Aalborg University called Heat Roadmap Europe: Large-Scale Electric Heat Pumps in District Heating Systems, together with our colleagues in Sweden at Halmstad University, where we created a survey and a review of the large-scale heat pumps in district heating systems with a capacity of at least 1 megawatt thermal working, as I said, in the district heating system. The study is available online on the web address over here, but you will get access to the slides after this presentation, so you can access it and find out more about it. In this following slides, I will say more about some of the highlights of this study, but also related studies on large-scale heat pumps that are interesting to know about. And I will start with the capacities and the market development. As we can see from this slide, on the top left side, the largest capacity nowadays installed is in Sweden. Actually, in fact, the total capacity installed in Europe is approximately 1,600 megawatts thermal. So out of this capacity, 1,200 are installed in Sweden. We can also observe, though, that most of this capacity, approximately 1,000 megawatts, is represented by old heat pumps that were built in the 1980s, and some of them have over 30 or over 35 years old. So one could say they're quite far away from their expected technical lifetimes. Nevertheless, these heat pumps are still functioning, and there's no plans on decommissioning this entire capacity. The reason why Sweden has so many heat pumps installed in district heating is because of a structural surplus of electricity that occurred in the 1980s when numerous nuclear power plants were built. Given the low priced electricity and then the surplus electricity, the states offer grants and subsidies for the construction of power to heat solutions, such as heat pumps or electric boilers. So if in some cases, in this case, heat pumps managed to be deployed on such a large scale in the 1980s, maybe this can happen again when we have surplus electricity in the energy system. Nevertheless, looking forward in this slide, heat pumps are not just in Sweden. They're also in Switzerland, Norway, Italy, Finland, France, and Denmark. In total, we managed to identify heat pumps in 11 countries across Europe. And there are no less than 150 heat pump units spread across Europe. The graph on the right side shows that in the 90s, the capacities installed decreased quite a lot compared to the 90s. But after the years 2000, and more specifically after 2005, 2006, there was an increase in the capacity of the heat pumps, the total capacity, but also in the number of units, which also created a situation where the average capacities of heat pumps were smaller, 3 to 9 megawatts thermal, compared to what was before in Sweden, with average capacities of approximately 13 to 19 megawatts thermal. Heat sources are a very important part in this story. There's quite a variety of heat sources for the heat pumps that we managed to identify in our survey. There's sewage water, ambient water, industrial waste heat, geothermal, flue gas, district cooling, or solar heat storage. Now, sewage water, as you can see, has the largest capacities. There are 54 examples found in Norway, Sweden, Finland, and Switzerland. And it has been in use since the year 1981. Approximately 56 of this installed capacity in Europe, out of the 1,600, 56% is heat pumps using this type of heat source, sewage water, and has a temperature range between 10 and 20 degrees Celsius. Also worth to mention is that the sewage water used by the heat pumps is generally treated before use as a heat source, except for some examples in Norway. The second type of heat source, the ambient water, is represented by the lake, river, or seawater. And it has 34 units with approximately 390 megawatts thermal. And this represents 24% of total capacity with an average of approximately 11 megawatts thermal per unit, and the temperature range for the heat source of 2 to 15 degrees Celsius. Industrial waste heat comes from various industrial processes. But this type of heat source is also quite similar to the geothermal heat in terms of temperature ranges between 9 and 55 degrees Celsius, so quite a wide range. Comes with similar average capacities per unit, and overall similar capacities installed nowadays. Worth to mention in this case of industrial waste heat that a study made in Sweden by Sven Werner and Helge Abelfag has managed to identify that this heat source has the largest heat production decrease over time, and that represents approximately 300 megawatts thermal that were decommissioned over time. All right. There's also flue gas, district cooling. District cooling is very interesting since it's a heat source used by the heat pumps connected to the return pipe of a district cooling network. There are examples in Sweden, Finland, and Denmark. And this heat source, this type of heat source, also brings some interesting examples. Like it also has temperature for the heat sources of between 0 and 9 degrees Celsius. For example, the heat pump in Høje Taastrup in Denmark has the lowest temperature for the heat source in the survey, which is only 0 degrees Celsius. There's also the solar heat storage, again with examples in Denmark, approximately 4 megawatts thermal, and temperature ranges between 10 and 35 degrees Celsius. I'm using the word approximate for all these capacities and numbers because it's very likely that we haven't managed to identify all the cases in Europe. There's likely to be more. So this is the minimum we have managed. With the minimum we have in Europe nowadays, it's very likely there's actually more, but we haven't found out about. Now, these heat sources are quite varied, and we try to rank them in a way to see which sources have the highest potential for the future. As you can see from the graph, sewage water has the highest potential, and that is because it provides generally high temperatures, 10 to 20 degrees Celsius. It provides stability and security. For example, in this case, the investments in the sewage system of a city are long-term investments, and it's very certain that that heat source is there to stay, compared to, for example, industrial waste heat, which is much more dependent on the business supplying it. And of course, it is the proximity to the urban areas. Sewage water is located in the proximity of urban areas, making it almost an ideal heat source to use. And we can see that more than the half of the heat pumps in the survey are actually using this type of heat source. Of course, it's also the ambient water. Doesn't provide the highest temperatures, but it provides stability and security. It's a heat source that is there to stay, and it's in many cases located in the proximity of urban areas. I'll now say more about the other heat sources. I think it's quite clear what are their advantages and disadvantages. So I'll go forward to the next slide on refrigerants. For the refrigerants, most of these refrigerants, as you can see from the graph on the left, are synthetic refrigerants, more specifically the hydrofluorocarbons. Now, these refrigerants are used by most of the heat pumps, but the disadvantage for them is that they have a high global warming potential, and that is a potential of 1,300. It's a factor of 1,300 higher than the CO2. And I'm not referring to the CO2 as a refrigerant, but the CO2 emissions. However, options and variants exist to replace this refrigerant and have different types of heat pumps, and that would be heat pumps using ammonia, carbon dioxide, isobutane, or hydrofluoroolefins. I will say a few words about these refrigerants, so you get a better overview of their advantages and disadvantages. So ammonia is a refrigerant generally used in medium and large-scale applications. It can work at temperatures up to 90 degrees Celsius, such as the Dragon heat pump plant in Norway, and can have a COP of 3 or even over 3 quite easily. Its efficiency is comparable with one of the synthetic refrigerants analyzed in the survey, but it's also moderately flammable and toxic, so requires some specific safety precautions. In the survey, we managed to identify 26 units using this refrigerant with a total capacity of 51 megawatts thermal, with some of the oldest units in the survey operating in Lausanne in Switzerland since 1986. Carbon dioxide. It's a refrigerant which is non-toxic, non-flammable, and non-corrosive, and is generally obtained as a waste product, making it quite a cheap refrigerant. However, the downside of this refrigerant is that has to work at high pressures, making it less suitable for large-scale applications. And here I mean larger than 1 to 2 megawatts thermal. There's only one example of a large-scale heat pump using CO2 refrigerant in the survey, and that is in Denmark again, in the Marstal district heating network, and it has a heating capacity of 1.5 megawatts. I mentioned the hydrofluoroolefins, and this is a synthetic refrigerant, and it's also known as the fourth generation of refrigerants. They're similar to the hydrofluorocarbons I mentioned earlier, as they contain the hydrogen, the fluorine, and the carbon atoms. But unlike the hydrofluorocarbons, they have a global warming potential of only 4. They are a possible replacement for the hydrofluorocarbons due to their similar thermodynamic properties that allow the application of large-scale heat pumps, such as the ones built in Sweden in the 1980s, but generally have a reduced efficiency compared to the hydrofluorocarbons. And this, moreover, these refrigerants are contested in some situations, in some circles, because of the toxic substances they release in case of leaks and after their breakdown in the atmosphere. And this is an important topic to discuss because the refrigerants, such as the hydrofluorocarbons, are set to be phased down by 2040, following the amendment to the Montreal Protocol, which was the amendment was signed in 2006, which actually will phase down these refrigerants in most of the countries by the year 2040. So it's likely that many of the heat pumps in use today cannot be retrofitted with new refrigerants such as this one. So new capacity would have to be built, but most of the heat pumps are also very old. Most of the capacity is very old and isn't there for more than 30 years. Yeah. Another hot topic is the operating temperatures and the COPs of the heat pumps. Now, contrary to the general belief, most of the heat pumps can actually provide and supply temperatures between 70 and 80 degrees Celsius, or even more than 80 degrees Celsius, with COPs of over 3, in many cases 3.5, 3.7. As you can see from the graph on the bottom, from the table on the bottom, the lower the supply temperature, the higher the COP, and the same applies for the heat source. The higher the temperature for the heat source, the higher the COP of the heat pump. Yeah, as I mentioned, the heat pumps can provide temperatures can provide COPs between 3 and 4, And that is also the case for the heat pump in the picture, the one in Gothenburg, which can achieve these COPs even though it was built in the 1980s. So if technology that was actually built in the 1980s can provide already this kind of COPs, nowadays the new technology can easily provide COPs of 4 to 5, as I will show you in the next slides. The operation of the heat pumps is also was also researched in this study, and not only in our study, but also in other ones where the heat pumps were the center of attention. Now, heat pumps are expected to have a main role in the future, as they should be able to accommodate large shares of variable renewable electricity. So a concern is the mechanical wear that appears during startups. The experiences from Sweden show that the daily startups are close to the limit of normal operation, but still acceptable for large electrical engines, which are generally the most vulnerable part of the heat pump. For example, again, the heat pump in Gothenburg, the very old heat pump in Gothenburg, has been operated strictly with regards to electricity prices since the beginning of 1990s. With few or no mechanical issues because of this way of operating it. All right. The connection to the district heating of the heat pump is also important to know about. A study made for the potential of installing heat pumps in Copenhagen showed that if heat pumps are connected to the distribution network, they can have a higher COP and also more operating hours than if they would be connected to the transmission grids, when they will have lower COPs and less operating hours. However, the downside of connecting a heat pump to the distribution grid is that it can only supply a limited area, while if it's connected to the transmission network, then it can supply a larger area. Of course, heat pumps are dependent on electricity prices and biomass prices and fossil fuel prices. And the graph on the right-hand side is quite revealing in this sense. The higher the price of electricity, the higher the price of the cost of the heat. And this relates to what I said before, that the heat pumps should be used in the future where there's high amounts of variable renewable electricity. So in our perspective, heat pumps should be used in times of high electricity production to supply the heat demand and also to supply the heat storage, as seen in the picture on the left. Whilst in times of low electricity production, renewable electricity production, then the CHP production can kick in, and together with storage or only storage can supply the required heat demand. So this actually shows the desired flexibility we would like to have in a future energy system. Then, to conclude what I said previously, we have some opportunities with heat pumps, and also we have some barriers, some threats. Heat pumps can increase the flexibility of the energy system through the very important sector coupling, which brings the synergies and reduction in investment costs and operation and maintenance costs in some cases. There's also the high efficiencies they can provide with the COPs between 4 to 5, and they can take advantage of the low-cost electricity prices. They also have a multitude of conventional and unconventional heat sources. As I showed earlier in the slides, there's many heat sources to use which are actually not used today, both renewable heat sources or waste heat sources from various industrial processes. And of course, the heat pumps can benefit from being used in the low temperature district heating systems because of the increased efficiencies they can achieve. However, there are some threats over here, and an energy market without the carbon price is not varying. stimulating for the deployment of large-scale heat pumps, and the same is when subsidies for biomass and fossil fuels are offered. In some cases, and maybe Thomas can tell us more about it, about the willingness of some policymakers to remain technology neutral. There's also high investment costs for heat pumps in general, at least compared to competing technologies. But prices have decreased quite a lot in the past years. And the last but not the least is the lack of knowledge on the technology maturity. And this is actually the aim of this webinar, and also of our study on the large-scale heat pumps, is to increase the awareness and the knowledge on what heat pumps can actually do nowadays. Yeah. And I will end with some case studies, and the numbers over here, they can kind of speak for themselves, but I will just try and sum it up. So this is cases of some heat pumps that could be installed in Aalborg. So what we can observe from this numbers is that the lower the supply temperatures that they have to supply the heat pumps, the higher the COP, and the same the higher the heat source, then the higher the COP. And in some cases, the heat pumps can have a COP of 10 if are using high temperature heat sources, and also are supplying in low temperature district heating systems. Another example from Denmark, in the city of Aarhus, shows some similar results. In any case, this before I end, I also want to show some interesting literature that some of you may be interested in reading. These are studies that have as a central role heat pumps, but also the last one is a study on the risk of industrial heat recovery in district heating systems, which is quite revealing, showing that maybe industrial waste heat recovery is not such a risky business case in the end. But that is all from our side.
Thank you very much, Andrei. I would like now to move on to our panel discussion and welcome Thomas Novak from European Heat Pump Association. Hi, Thomas. Thank you for being with us. I would like a first comment from your side, and as I suppose you can respond to what Andrei mentioned earlier.
Yes,
Thomas?
Good afternoon. Can you hear me now?
Yes, thank you very much.
Very good. Well, thanks, Brian and Andrei, for the good introduction. I have seen a lot of positive notions. I will just comment in a few ways on it. I saw that in this picture that you showed, the smart energy system, heat pumps are at the center. And Brian, you said that heating must be at the center of the decarbonization, and we fully agree from an association's perspective. But we also think that, as you show it so nicely, heat pumps is probably one of the technologies that should be at the center of this future energy system, together with the other ones that are shown. What we see in Europe overall is that the heat pump market is growing quite strongly now. We had 2 years of double-digit growth. 2017 is not counted out yet, but the first indications show that we are very close to 10% again. So among the different renewable energy technologies, heat pumps is actually doing quite well. What is not covered in this project, but I think is worth mentioning, is that heat pumps can operate also in individual buildings and in commercial applications. And then they are usually in a much lower capacity range. So normally in an individual building, we are around 10 kilowatts. In commercial applications, around 50 to maybe 200 kilowatts. And from our perspective, the large heat pump category starts at around 200 kilowatts. What was also not mentioned, because it's not the scope of today's presentation, but I think it's still very important, is that air is a very reliable energy carrier, also for heat pumps and also for large heat pumps, not for the megawatt scale, but at least for the commercial ones. And we have seen in the last example that Andrei has shown that Aalborg is thinking of having a couple of 50 megawatt units. This is, of course, good from a cascading perspective, so you can vary the capacity that you need. But these type of heat pumps also operate with air, and then they can achieve the same efficiencies. Maybe for the audience, it's also important to stress that the efficiency depends a lot, and especially in this application area, it depends a lot on the energy demand that you need and on the temperature level that you need. So the distance between the temperature of the energy source and the energy sink is the single most influencing factor on the efficiency of the unit. I would agree that also from our perspective and from our experience, the normal efficiency in industrial applications, not only COP, because COP is a lab value, but also in a seasonal perspective, so in real-time experiences, the efficiency of a heat pump system can be above 3. And for most application areas, that is very good and that's very nice. One thing that I thought was noteworthy is that you showed, Andrei, that in Sweden, the biggest heat pump increase in large heat pumps was when they had surplus electricity from cheap electricity sources. So I'm very eager to see if Denmark will follow this, because Denmark is one of the most ambitious countries when it comes to providing generators that will eventually, in the very near future, provide a lot of additional electricity at very competitive prices. So yeah, I think overall there is a good future for heat pumps. I would like to add one thing on the literature side. We, as EHPA, we create an annual heat pump outlook, a heat pump report. You can find that at the website stats, like stats.ehpa.org. And also for those of you that want to learn more about small and large heat pumps, we have 2 conferences upcoming. We have a Decarb Cities conference in Vienna on the 16th of May, and followed right after on the 17th of May is the Large Heat Pump Forum, the Middle European Large Heat Pump Forum. That's also in Vienna. So if you have an interest in going there, just let me know, and I'll send you all the information. I keep it for that, for the initial comments, and then looking forward to the discussion.
Thank you very much, Thomas, for your supplementary information. Do we have a comment from this, Brian?
Yes.
Yeah,
thank you, Thomas, for your feedback. I think it's nice to hear that our project is useful in that sense. Maybe just to clarify, what we try to do is a comprehensive heat strategy, which includes both large-scale and small-scale heat pumps, air source and other source heat pumps on the heat strategy side. But we also stress what the role of the different technologies are, both large-scale and small-scale heat pumps, and also within district heating, what the role of large-scale heat pump may be. And in this sense, the temperature levels, of course, become important, but it also becomes important to know that a heat pump is not able to provide all of the heat, but is in combination with other sources, and a technology that can enhance the temperature levels of industrial waste heat to cover maybe 15 to 25% of the district heating demand, together with other renewable energy sources.
Yes. Now we can go to our first question for the day. I think there is one for you, Andrei. Ana Marquez is asking a question about sewage heat pumps. She says, I guess that they are not viable in countries with milder climates due to lower temperature differences with the outside temperature. Is there a rule of thumb that can be used to include or exclude heat pumps in early assessment of heat sources?
That's a good question, Anna. Thank you for it. Well, I have a simple answer for you, and that is that in this study we just index which are the heat sources and what are the current examples. Of course, there has to be an assessment of the potential in each of the situation, but you have to be probably more technology specific people that can answer to you on this question. What we do know is that in many cases, and not just Sweden, but also Switzerland, which is not exactly a cold country all the time, such heat pumps are being used, and they're using sewage water, which has a constant and rather high heat source temperature. So if this can be done in one place, it's very likely can be done in other places. We should not generalize, but it can be replicated in many situations.
Right. Thank you. There's another question from Eduardo.
John, can I just comment on
that? Yes, please.
Because I think I can support what Andrei said. From our perspective, sewage heat pumps can be operated everywhere in Europe. If you need heating, you can operate a sewage heat pump. Even under certain conditions, if you need cooling, you can operate a sewage heat pump, but that would probably require a more thorough assessment. And if you need more information about proper examples that are even below the 1 megawatt range, because I think that is something we need to stress, that what Andrei presented was 1 megawatt and above, but there is a number, and quite a much bigger number of heat pumps that are in the category between 200 kilowatts and 1 megawatt, because there is many more application fields that need this type of capacity. So probably what Andrei and his colleagues did was that is something that you can handle, because you cannot count every other heat pump that is installed. But the application field is actually enlarging very much below this 1 megawatt level.
Yes, thank you for the comment, Thomas. We can now move to the next question by Donna Cartland. Have any of the speakers any knowledge on the typical COPs of heat pumps recycling wasting heat from air-cooled data centers to supply around 80 degrees?
I suspect that there are no publicly available data on this at this stage, but I do know that there are quite a lot of efforts on, let's say, assessing what the role of this could be. I know that that there are several Danish cases in Viborg and Odense that are dealing with this, and there are also several cases in Sweden where they are assessing the use of heat pumps to provide heat. So the knowledge is there, but we do not have them in our team.
But I can say that that I have just had the opportunity to visit such a heat pump in the United Kingdom. It was a data center for a hospital, and it was connected to the hot water system of the hospital. And it's again something like it was 50 kilowatt of heating supply, so rather small unit, and the efficiency at providing 80 degrees for the hot water system was above 3, and that is quite typical. You would imagine that, because the waste heat temperature of from the cooling of the data center is around 42, 43 degrees, and then if you have a delta T increasing the temperature to 80 or maybe even 85. And in this case, they used CO2 as a refrigerant. Then it's typical, and it's to be expected that the efficiency is slightly above 3. And there is many more cases. So again, if you need solutions for this, just get back to us. Maybe I can say I'm also part of the team because we're in the Heat Roadmap Bureau, but you can contact me directly and I can provide this information.
I think the question here also relates to the district heating part, and here I would expect that we could have a larger COP than 3, and I think if we really want to use data centers, we need to combine it with larger heat pumps and larger district heating systems.
Oh yeah, but you can. There is an example in Finland. It's a company called Kalefa, and they have done such thing. They have connected the data center to district heating, and I don't know the COP by heart, or the SPF by heart, but normally if it's below 3, people don't do it. So you can say if such a system has been built on commercial terms, usually the efficiency is at least 3.
All right, time is running, so we'll have 2 more questions. The one now is from Rim Resky, saying that in Sweden, the increase in heat pumps installations was correlated with the building of nuclear power plants in the 80s. Was or is there a similar trend in France, considering its nuclear policy?
That's an interesting question, but I wouldn't say that the construction of heat pumps should be correlated with the construction of or the capacity of nuclear in one other country. The reason why we had and we have so many heat pumps in Sweden is because there was a surplus electricity, not because it was just nuclear. And surplus electricity can also come from variable renewable energy sources, and that is actually the aim and that is what we should achieve with the heat pumps. They should provide the flexibility of integrating renewable energy sources, not nuclear. We don't really see nuclear as a solution, especially in such cases the heat pumps would be supposed to work on a base load continuous operation, which would not have any role in this case for integrating renewables.
All right, and then we move to our last question for today, and that's for Eduardo Aventano, saying that asking, have you done some comparative analysis between Carnot cycle heat pumps versus Libre absorption heat pumps?
I can answer that. I can first say that we only looked into the electric heat pumps, not absorption heat pumps, and the COPs that we found are based on literature reviews, either from the manufacturer brochures, for example, or other communication, or from actual examples of installed for the installed heat pump. So we haven't done this comparative analysis between the Carnot cycle and the Libre absorption chillers.
Thank you, Andrei. At this point, I need to close up. So thank you all for your participation. The recording will be soon available on our website and YouTube channel. We look forward to having you at our next webinar on 19th of April, where Bas van Ulen from Utrecht University will talk about energy savings and synergies within industry. You can visit our website to get to know more about the project and follow us on Twitter to stay updated. Thank you for attending and have a nice afternoon.